In this example, we will antidifferentiate 1 divided by the square root of x squared minus 6x plus 13. Now, my intuition on this problem is at first glance it might look quite difficult seeing this kind of just random quadratic in the square root in the denominator of the integrand. But the observation to make here is that if we use a bit of algebra, i.e. complete the square in the denominator, then we will hopefully be in this ideal situation where we can apply a trigonometric substitution. So let's go ahead and do a bit of algebra to the side here and complete the square. So if we think of x squared minus 6x plus 13. So I'm going to kind of skip ahead to what I want this to look like. I want it to be x minus some number squared, and then plus or minus another number after. Looking at the coefficient of x, we say, well, this would be, the x squared minus 6x would be the first two terms of x minus 3 squared. So I'm going to need a 3 to fill in the blank there. So that would be x squared minus 6x plus 9, and 13 would be 9 plus 4. So x minus 3 squared plus 4. So rewriting our integral, it would be 1 over the square root of the quantity x minus 3 squared plus 4. Now looking at our integrand, seeing this x minus 3 squared plus 4 is an indicator that we want to use a trigonometric substitution. And looking at it, we think, well, I want to take that x minus 3, and ideally I would like that to be my substitution. So in this case, something squared plus 4, so the substitution will be 2 tangent theta. So x minus 3 is 2 tangent theta, so that x is 3 plus 2 tangents of theta, and dx becomes 2 secant squared theta, d theta. So putting this all together, in the integrand, the x minus 3 is going to be 2 tangent theta, so we'll have 4 tangent squared plus 4, and the dx is 2 secant squared theta d theta. Then note what we have underneath the square root in the denominator. Well, that's 4 times the quantity tangent squared plus 1, and tangent squared plus 1 is secant squared. So this would be 4 secant squared theta, all times 2 secant squared theta d theta. And now just doing a couple cancellations. The 4 in the square root is going to end up as a 2 and cancel off with the 2 that's in the numerator. The square root of secant squared is simply secant, so that's going to cancel off one of the secants in the numerator, and the new power there is going to be 1. So we're left with simply the antiderivative of secant. And this is a common antiderivative formula that we need to know. We've encountered it multiple times. So this would be the natural log of the absolute value of secant theta plus tangent theta. And now our last step is to get everything back in terms of that original variable x. So we go back to our substitution. X minus 3 is equal to 2 tangent theta. So that's equivalent to saying x minus 3 over 2 is tangent theta. And once again, we just draw that associated right triangle. So if we have our angle theta, tangent of theta is x minus 3 over 2. By the Pythagorean theorem, we can label the hypotenuse then as the quantity x minus 3 squared plus 4, all underneath the square root. So looking at what we have here, natural log of the absolute value of secant theta, so that would be the quantity square root of x minus 3 squared plus 4, all divided by 2, plus tangent theta, which is x minus 3 over 2. and this is all plus c. Now, a very important observation to make here is that many integrals will require multiple techniques of integration, and sometimes before we perform, in this case, the trigonometric substitution, we might have to do some algebraic simplification, like we've done above here with the completing the square, or we may even have to do another substitution or another technique of integration.